Testing on YouTube. Test, test, test. Testing, testing, testing. All right, it works. How's it going? Open Room XYZ and Yamal Boussouf, 8254. Let's test it on X. Testing, testing on X. Oh. What are we in today? We got a couple cool things today. Let's make sure the volume works on X though. I tried to fix this microphone, but if it drops out, we're going to have to do the headset trick again. All right, perfect. Let's get this started. Welcome everybody to another Hoopos stream. Today we're going to be doing a little bit of coding in the world of Kernel RL. So kernel reinforcement learning, we got a nice little pic here generated by, I think this is IdeaGen or whatever it's called, 4 out of Google. But we got our white Bengal cat on top of a sloth. How's it going, Julien and Dark Matter or Dank Matter? Jamal Boussouf, check this paper, the superweight and large language models. Maybe. I think we got a little bit too many papers going on right now, though. So this is a reference to this. So today we're going to be doing matrix multiplication kernels. Right, so why matmul? Transformers spend most of their flops inside matmul. So the linear layers in the MLP or the FFN, the attention, QKV projections, output projections, all of those are basically matmuls, which means that matmuls are the most important operation, floating point operation that is done inside GPU. So if you can get that to be done a little bit faster, then you can speed up everything from training, inference, whatever you want to do. These operations are embarrassingly parallel, making them a natural fit for a GPU. So I think if you're watching these streams, you probably already know how matrix multiplication works, but here, let's say you have a matrix A, matrix B, right? You take the row of matrix A, the column of matrix B, you do A1, B1, A2, B4, A3, B7, add them together, you get C1, right? So this is the simplest implementation of a matrix multiplication, and this is implemented in a kind of naive serial way. So if you had a CPU that was basically going to do every operation in sequence, it's just 2 nested for loops with a nested for loop inside of that to add up the A and the B, and then you end up assigning that to C, and that's basically the matrix multiply in the most naive way possible. So the question I guess we're asking is, could we use reinforcement learning to basically design a better version of this? And that's where I'm going to now introduce the second part of this thumbnail, which is this sloth. We're going to be using this startup. I don't exactly know what to call them, a software startup, machine learning startup, but basically they make these kind of like training recipes or notebooks, if you want to call them that. And they released this one here. So this is GPT OSS 20B with GRPO. So GPT OSS 20B is the smaller open source version of the GPT open source, I guess, model, which is probably not exactly their model, right? It's like a kind of a slightly different variant. But in this notebook, they train or try to use reinforcement learning to push gradients into a low rank adapter that makes it better at creating matrix multiplies, but they're not. It's not really matrix multiplies, because the way that it's actually being done is it's being done entirely in Python like this, right? So this is the actual prompt that we're trying to improve. For example, create a new fast matrix multiplication using only native Python. You are given a list of numbers, output your function. So basically we're trying to find a couple lines of Python, and pretty much all the solutions that it ends up coming up with are these like kind of nested list comprehensions, which aren't ideal, right? These type of things. This is basically just nested for loops, but written in a way so that it's in one line of code, but usually not advised. But can we use reinforcement learning to get GPT OSS 20B to basically generate better and better versions of these? And that's what this notebook is doing. So that's what we're going to be looking at. Paper reading or code, a little bit of both. I have some papers that relate some stuff. It's almost more just like an exploration. I have slides if you want it to be that way. So maybe let's do a little bit of a summary here. Actually, let's go into the actual thing. So first things first, right? The way that they present this code to you is in a notebook. It's not super usable. So actually, the first thing I generally do here is I come down here, or I guess there's like a download or something like this. Yeah, so you can download this, and then you could download it as a Python file instead of a notebook, right? So the advantage of the Python files, you can just run it. So that'll give you this, right? This is the kind of unformatted dump of the Jupyter notebook, and you can see here this is not ideal. You got a bunch of imports kind of like scattered throughout here. A lot of this code is really just for kind of printing things, demonstrating some stuff, which we don't really need in an actual training script, right? So the first thing I'm going to do is I'm going to turn it into kind of a more standard Python script, and I'm going to pull out all the variables, right? So all these magic numbers, all these different hyperparameters, such as max sequence length, the LoRA rank, the random state, the learning rate. I'm going to basically pull those all out into this config object here, which I'm calling the training config, and that's going to make it easy for me to kind of modify these numbers and kind of test and tune this script. Okay. Julien asking the question, so like GRPO training, reward function is verifying the correctness of the map mall. That's a very good transition, Julien, because what are we actually going to use as a loss function for this reinforcement learning process? And that's where reinforcement learning is popular now, but people are kind of forgetting that it has kind of a pretty big flaw, even in this realm of verifiable rewards. So, and that's something that they address in their documentation here. But if you actually look at the script, what is the reward function? This is the reward function. It's a composite reward made up of 4 independent components. Okay. So it's like one of those like multi-part loss functions. It's kind of the same thing here. You have a multi-part reward function. And for example, part of it is going to be whether the function works, whether the actual little matrix multiply Python function is actually valid. -2 points if you have an invalid function, -0.5 if you try to create the function and it fails for some error, +1 if it succeeds, right? You have, for example, no cheating. So discourage importing non-standard lib modules. So basically what ends up happening is that the model tries to be a little clever. It tries to basically cheat or find a way around the specific requirement that you've given it, and it says, okay, well, I can just import a NumPy matrix multiply and then just use that. So we have this term in our loss function that basically says -20 points if you import torch or NumPy and then just use that one, right? Heavy penalty dominates to strongly prevent cheating. Then finally, you have kind of what we actually care about, which is speed check and correctness check. So correctness is making sure that you get numerically correct output. So is the actual matrix multiply producing what we would actually expect out of this matrix multiply? You know, you wouldn't necessarily want it to basically typecast everything to an integer and then just it's faster because everything's a very low precision data type, right? So you kind of want it to actually matrix multiply without losing the accuracy of the result there. And then finally, speed check, which is almost what we really want to optimize for, which is how fast is this, right? But off the bat, you can already start to see the problems with this, right? So the problems with this, and kind of one of the harder things about reinforcement learning, is this kind of reward engineering, right? So look at all these numbers here: -2, +1, -20, -6, +6, -10, +10. These are all effectively arbitrary, right? So some random human picked these, and picking the right numbers here is basically impossible. It's a incredibly large search space, right? So I actually pulled out all these numbers. So here's all the numbers. And how do you pick the right ones for these? You don't really know. So you just kind of have to make up some numbers and kind of tune them a little bit, but the numbers you're going to make up are not going to be perfect. And then whenever you tune them, you're only going to get to explore a very small part of the search space of possible values for these. So that's one of the hardest things about RL right now, is this kind of reward function engineering. And just to kind of show you that this problem has been around for a while, this is the original OpenAI DOTA 2 with large-scale deep reinforcement learning paper at 2019, so quite an old paper at this point. You can see some of the classic names on here. We got Ilya, we got Greg. So in this paper, right, they just kind of solve Dota 2. They get an agent that plays this kind of a MOBA video game, right? But I want to scroll down to page 44 here. I think we're deep in the appendices. Look at this. This is effectively the same thing that we just looked at here with this unsloth multi-part reward function with these kind of arbitrary numbers. Here's the same exact thing for the Dota 2, right? So if you win, you get 5 points. If you gain experience, you get 0.002 times that experience. If you gain gold, you gain 0.006 times the gold, right? So the same problem that we have here, right? Why 5? Why not 6? Why not 10? Why is gold 3 times more important than XP, right? Why not 5 times more important than XP, right? And kind of the same way that we're never going to sufficiently explore the space of possible weights for these reward functions that are multi-part, OpenAI didn't explore this space either, right? They just kind of like picked some values that kind of made sense. Maybe they got the guy who plays a lot of Dota to kind of give them good initial values. Maybe they adjusted them a little bit, but we're largely just kind of hoping that these work, right? So I thought that was something important to talk about. Enlarge the font, please. All right, I'll make it bigger, guys. Sorry about that. All right. All right, what else can we now talk about? Let's talk a little bit about exactly what we're doing here. So what we're actually doing here is we're training a LoRA adapter, right? So you guys have heard me talk many times about this before, but whenever you're fine-tuning a model, and this is what we're doing now, we're kind of doing this, right? So this model right here, GPT-OSS20B, the majority of its training, right, this one here, is this white bubble here, which is pre-training compute. And all we're going to do in this Python script is we're going to basically add a little bit of RL compute. So that's really what we're doing here, is we're adding a little bit of RL compute to a model that already has most of the intelligence, right? And the way that we do that is with this LoRA, right? So the LoRA has a specific rank, which effectively tells you the size of these A and B matrices, right? And because of the magic of matrix multiplication, this inner dimension kind of melts away, right? So if your A matrix and your B matrix, which are the only ones that you're pushing gradients into, right? And these are going to be smaller than your actual weight matrices. So the whole point of LoRA fine-tuning is that these are smaller, and thus they're going to be faster to train. The gradients, all of those things are going to be less memory, which means that you can train them on smaller GPUs. But this R here, which is kind of the width in between the A and the B, somewhat determines the intelligence, I guess. So if you have a very small LoRA rank, right, your bottleneck is very, very tiny, which means the intelligence of this is probably not going to be as much as if your bottleneck is larger, right? But the larger you make that bottleneck, the more weights there's going to be in A and B, the bigger the gradient is going to be, the bigger the optimizer state is going to be. So while we're talking about LoRa's, one interesting kind of thing that popped up is this here. So we finally got something out of Thinking Machines. If you guys remember, Thinking Machines was Mira Murati, which was, I think, who was the CTO of OpenAI at one point. Basically, she left, and then she created this new Thinking Machine startup, which got a huge amount of money. Nobody really knows what the hell they were doing, and then now finally we have some idea of what they're doing. And it seems like what they're doing is LoRa fine-tuning. So they released this, what they call Tinker API, and Tinker is basically a way of LoRa fine-tuning specifically the Qwen and Llama series, including large mixture of experts model, like the 235B Qwen 3. So kind of an interesting, maybe they're showing, they're letting us peek into the curtain of these frontier labs and what the people at these frontier labs have learned. So I think it's kind of interesting. Here's a random quote from this guy who's a research scientist at NVIDIA. He says, if Thinky is saying you can just rank one LoRa all your RL training and model merging generalizes, are we saying that RL can be a series of independent rank one adapter trains for each capability and then just quickly stack all the LoRa's at the end? So what is he trying to say here? So if you can just rank one LoRa, so a rank one LoRa is kind of saying, okay, a LoRa, right, a low rank adapter with an R equal 1, right? And if you remember, the R is effectively how much intelligence you're putting in there, right? You're controlling the width of the model, right? The width is kind of like the representational capacity of that, right? The larger the width, the more nuanced and interesting the representations can be in this side, this LoRa. So LoRa rank 1 would basically be the lowest possible, fastest possible LoRa you could train. Model merging generalizes and a series of independent rank 1 adapters. So what he's referring to there is that something that people do with these LoRa's is they combine them, right? So maybe you have a LoRa that modifies GPT OSS 120B to make it better at writing these matrix multiply kernels, and then you have a different LoRa that makes GPT OSS 20B better at writing poetry. You can merge those together, and maybe if that generalizes, right, if you can basically keep doing that for arbitrary tasks, maybe you could just train a huge amount of rank 1 adapters on different tasks and then just stack all of them at the end, and now suddenly you have a model that is generalizes to all these different task distributions. I don't necessarily agree with this, and I have some data to prove that, or at least to justify my claim. So here's my data. So first things first, right, I took this script, or this Jupyter notebook, I converted it into this Python script, I pulled out all the hyperparameters into this config to make it very easy to train. And then the first thing you pretty much always want to do is you basically want to try it with the base hyperparameters, right? So don't touch anything and see if that works. And we're going to kind of go through the little Wannabe experiment that I have here. So this is basically runs. And you can see I start off with that one, and there's a bunch of different plots here, right? So these plots are chosen by, I think, unsloth. Unsloth makes the GRPO trainer. I think they might be actually using the Hugging Face GRPO trainer, this one here, right? But lucky for us, they've kind of logged a bunch of different things here, and I'm going to point out the important things here. So, for example, obviously you want to look at GPU memory allocated, GPU time spent accessing memory, and GPU utilization. We're going to dive a little deeper on these later in the stream and see how these are not always necessarily the perfect thing to look at, but you can see here that at least with these settings, vanilla settings out of the box, we're utilizing 70% of the GPU memory in my 3090, which is pretty good, and then we're also making heavy use of the GPU. So GPU utilization is almost more these are aggregate metrics. So GPU utilization is already kind of an aggregate metric, and then you're kind of, so it's already metrics on metrics on metrics. But you can see here that seems fine. Okay. And then here in the train, it starts to get kind of complicated because as we saw, we have a ton of these different reward function terms, so that so we have a bunch of different rewards here. We have speed check, and then we have the standard deviation and the mean for the speed score. We have the function works means, but we really just want the standard one. So this is the train reward. This is the one that we're going to be looking at here, right? So this is like all the rewards combined, right? So this is the combination of all these rewards. So I try that. You can see here I'm doing a couple different runs, and then I start kind of messing with the hyperparameters a little bit. But one thing that immediately jumps out to me at this is, so for example, this is the longest run that I had. This is a 19-hour run on my 3090. And what do you notice about here? So first of all, the reward does kind of slowly go up, right? So we are getting a slowly better reward as we're pushing gradients into this low rank adapter. In my 3090, it's a very small batch size. So if you actually see here, the batch size is basically 1. It's generating 2. So what that means is that we're using GRPO here. And I have the GRPO here, right? But the way that GRPO works is that it basically gets the advantage, or how good it's doing group relative policy optimization. So the group relative part is basically saying that in order to push the gradient, it's getting a couple different completions from an initial prompt, looking at the reward for each of those completions, and then basically using that to get the gradient to then push it into the actual LoRA, right? And then it has a little KL divergence on top of that so that you don't kind of drift too far away from the original model, right? So in order to fit this on my 3090, which is pretty old at this point, very small kind of GPU, kind of the limit of what you can do on a GPU, I would say. But you can see we only have 2 generations. So there's only 2 completions, 2 reward scores, and that's where the gradient is coming from. So it's not a super refined choice here, right? It's not like you have this giant batch size so you can push really good gradients in. A group of 2 is not great, exactly. But you can see it slowly gets better. But how does it get better? What exactly is it actually getting better at? And if you actually look at this, right, so you look at this is smooth, right? So I obviously, the background is the actual reward, and then this like bold line is the exponential moving, or the time-weighted EMA. So basically, it's like the average of the reward. You can see here that in the beginning, there's a bunch of these, you see these spikes that go down. That basically means negative 20 rewards. So the model either cheated or it did something bad, right? So we have these penalty terms such as -2, -20, -6, -10. And you can see that as the training progresses, there's none of these spikes anymore that are low, right? And this is kind of I think one of the problems with reinforcement learning is that reinforcement learning is not kind of as magic as people think it is, right? A lot of times what happens is that reinforcement learning just shuts off kind of parts, right? So the model has some probability distribution over the next possible token. And whenever you push a gradient with reinforcement learning, a lot of times what you're telling it is just don't do this, right? So you're basically giving it a very large negative reward for doing some kind of cheating, right? In this case, maybe it like imports NumPy and then uses the NumPy matrix multiply. You're giving it that big negative reward. And then what's happening is that all it's doing is it's just not cheating. And then if you just don't cheat and get that big negative reward, then your average reward is going up. Right? So I think this is kind of a microcosm of like what happens with, for example, RLHF, right? And this is why people will say that there's this kind of phenotype that once you RLHF a model, it kind of becomes much more narrow, and like it's not going to give you negative things, but the distribution of possible things that it can produce has basically been collapsed. and that more narrow distribution has a higher reward, but it doesn't necessarily mean that that model is better and can generalize better to other things. And I think there's something similar happening here, where really all we're doing in this process of pushing gradients with GRPO with this reward function is we're just kind of like getting it to not fuck up, and as soon as we get it to not fuck up, then the reward slightly goes up. So not necessarily ideal. High penalty suppresses exploration. Yeah. Okay. What other thing can we talk about here? So, yeah, I guess let me go into this. So the next thing, it's not Hoopo 100, it's Hoopo GPT OSS. I got a new code for you guys. So let me actually Control R. Right here, Hoopo GPT OSS. This code will get you 100 euros of free compute on DataCrunch, which is a cloud provider in Europe. So let's actually go ahead and do this live. We can hit this deploy instance. Let's do an on-demand instance. We're going to pay as you go, and we can pick out of these GPUs here, right? So far, we've taken the unsloth notebook, we've turned it into a Python script, we've run it, and we've confirmed that the reward does go up. But, you know, we're using really small batch sizes. It's kind of slow. We're training this at home. So now we want to go to the next level and train this on a bigger GPU. So we're going to use DataCrunch here. And you can see there's a couple different options. We have H100s, H200s, all the way to the fanciest machines that you want, but let's just say an H100, you can see here different numbers of GPUs. So for example, here, the 1248, what's happening there is that this is one H100, right? That one H100 sits inside this one kind of cooling wrapper thing, right? So this little box basically just contains the cooling infrastructure, the kind of like fan, or I don't even think it has fans, but it basically has molded plastic and fins such that whenever the air blows through it, it basically cools the chip. And there's 8 of these in one rack, and then there's multiple racks inside this data center, right? So whenever you're saying, I want a 8 H100, what you're saying is, I want the full rack, versus whenever you're like, I just want one X H100, or in this case, I guess a 1X H200, you're basically saying, I just want one of these, right? So you're probably going to be sharing that rack with other people that are using it. Okay, you can choose your pricing here, and you can pick the location that you want it. So I think last stream we picked Finland, which was up here, and this was the actual data center that we used, but you can actually also pick Iceland. So Iceland seems to be where they have the H200s. So kind of cool. And one interesting thing to look at that I thought was a little bit entertaining here is the temperature. So actually, if we look at this, right, let's look at these H100s and an H200. And now let's go up to the system and look at the GPU temperature. So look at this. This is the difference between a professional data center and my GPU at home. So obviously, my GPU at home is here in sweaty Texas, and you can see that my GPU at home is getting up to like 80 degrees, right? Versus the GPU at the Iceland data center, these guys are real cold. Look at that, 32, 40. These are icy GPUs over here. So I don't know, I just thought that was entertaining, the difference in GPU temperature between a professional data center and then a GPU training at home. Is Iceland cooler? Actually, I don't know. Let me see. I think the H200 is from Iceland. No, it's actually hotter. So the Iceland GPU is like hovering here, and then the 3 GPUs in Finland are slightly colder. There's a lot of details for that though, right? Because it has to do with the data center as well, right? So like it could be that the H200s in the Iceland are in like a different room, and that room isn't cooled as much as the H100s in the Finland room. But either way, I just thought that difference was quite interesting. Maybe they undervolt compared to gaming GPUs. Yeah, that's another thing you can look at. So, for example, you can look at the GPU power usage right here, right? So, interestingly, look at this. The 3090, so these right here, compared to the H200, the H200 uses more power than all of them, right? But look at that. The H100 actually uses less power than the 3090. And that's kind of like a mind-blowing thing that I think if you're if you understand computers, you probably already know this, but every generation of chips doesn't, even though, for example, the VRAM kind of keeps doubling, right? The flops keeps like doubling. So like there's kind of like Moore's law effects on like the actual memory and compute. The power usage doesn't actually change that much, right? So you can actually see here that like even though the 3090 is significantly worse than this H100, the power consumption is kind of about the same, which is kind of crazy, right? So future GPUs, not only are they much more powerful, but they actually kind of don't use that much more power, which is why, because we're in this kind of weird world where like everybody's worrying about power, right? The limiting factor for these giant data centers is power. If you actually use the most recent GPUs or the most modern GPUs, you're saving on the power as well. You're getting way more compute for your power than if you would have used older GPUs. So that's just one additional reason why people are very, very hungry for the latest GPUs and are just trying to buy a bunch of old GPUs. All right. Okay. It makes so much more sense to make the data center in a cold place. Yeah. That's why space is the ultimate frontier. I think the ultimate place to put data centers is in space, right? Imagine like a giant toroidal space station in the future that is just sitting there and has a bunch of solar panels, right? Solar panels are less efficient on the ground than they are in space because the rays don't have to go through the atmosphere. And also, we know from kind of Starlink, right, that eventually the lowest latency you will be able to get will be through the satellite because there'll be so much satellite coverage over the whole world that it'll actually be significantly faster, I think, and lower latency to actually have your inference GPU be in the space, right? So then your request is going up through the satellite into space, back down the satellite to your phone, right, or to the robot. So some people think that the future is going to look like a bunch of data centers in places like Iceland or Finland, where you have kind of like pseudo-subsidized power, maybe in places like Saudi Arabia, because they also have very cheap power, right? But I don't know if that's actually going to be the case. I think what you're going to end up happening is you're going to have a bunch of regulation around GPUs that's going to make it very annoying to actually deploy data centers on the Earth. So then people are just, and then at the same time, companies like SpaceX are going to drive the cost per kilogram into orbit down. So at some point, it's actually going to be cheaper just to have all your GPUs up in space using the free energy of space, and then there you go. Isn't there nothing to release the heat into space? I think space is very cold, but I do know what you're saying, where there's like you can't convect the heat away, right? So actually when you think about heat, there's three ways to lose heat. There's convection, conduction, and then radiation, right? So conduction is what's happening with the chip and then the fan or the heat sink on top of the chip, right? So the heat sink on top of the chip is sucking up all the heat from the chip through conduction, right? And it's metal because metal is very conductive. Then you have convection, which is whenever air takes away the heat from the heat sink. And in this case, usually it's forced convection, which basically means you're pushing air through, right? So you're pushing the air forcefully through those heat sinks, which is allowing them to cool off. But you also have radiation kind of heat transfer. And I think that's the one that works in space. So basically, any object basically radiates heat, and the hotter object radiates even more heat. So I think in space, you can't conduct it away. You can't convect it away. So you basically have to radiate it away. But That's just my thoughts. All right. Let's keep going here. What else did I want to show? Oh yeah, we were talking about exploration, right? So let's look at that. I thought this one was interesting. So I'm now actually no. Let's finish running this thing, just so you guys can do it. So we're gonna start an H200 in Iceland. We're gonna have Ubuntu 24 with CUDA 12. We don't want any storage here. We're going to give it the SSH key for this computer. We don't want any startup script. And again, if you want to use this code here, HUPO GPT OSS 100 free, you basically put it into here. So you would say add coupon, you would put that code, and then you'll get 100 euros. But in our case, we could just hit deploy now. I don't actually want, please fill in coupon. What if I don't want in the coupon? Okay. It should start up another one. I already have one instance running. But all right, there you go. So now we have two instances. We have the one that I have running for a while now in Finland, and we have this new one in Iceland. It's provisioning, but once that's ready, we can SSH into it. Okay. The impact of O2 on chips in a data center? What do you mean, of oxygen? So you're saying that oxygen slowly like corrodes the chips? I wonder if that's the situation, right? Ideally, if you really care about that type of stuff, you could have some kind of inert gas, like a noble gas, right? And then you could basically close the air, right? So you basically have everything inside this enclosed air that is pumped in with this noble gas. But I think at that point, you might as well just use liquid cooling, right? So I think that's actually where most of these data center cooling solutions are going, is that the heat sink on top of the chip is actually using not losing the heat to the air, it's actually losing the heat to the water, and you have this kind of similar kind of forced convection, except the liquid that is being forced over the actual heat sink is not air, it's water, right? Yeah. So this is actually kind of a little bit outdated at this point. Okay. There we go. See, it spins up pretty quick. Here's your SSH. We can copy that. And let's go into the actual here. Copy paste that SSH. Hit enter. Your computer's going to be like, I don't know what the fuck this computer is. Who's this? Is this okay? Am I okay connecting to this computer? And I got to tell my little computer, yes, I know this person. And then boom, there we go. Now we're in Iceland. See? Vidia SMI. There you go. There's our nice little H200 with CUDA 13. Got 143 gigs of VRAM, which is savage. And you can see here the max consumption is 700 watts. So even our usage that we had here with this H200, yeah, even this usage that we had here of like 350, that's still actually pretty low for the power usage. Okay. So here's the next thing I want to compare here. So let me actually visualize none. Then I'm going to visualize this one. And then I'm also going to visualize this one. So these are the two longest runs that I did. Let's sort, descending. So I have one run on a 3090, one run on the H200. And I actually kept the batch size the same, right? So I wanted to kind of directly compare the H200 to the to the 3090 with the same hyperparameters, except for one hyperparameter, and that's this one here, temperature, right? So the temperature is basically the randomness of sampling the next token, right? So whenever the model receives this prompt, right, you're going to calculate the KV cache for this, and then it's going to start autoregressively predicting tokens one at a time, right? So it's going to predict this token, and then this token, and then this token, and then this token, and then this token. This temperature basically allows a little bit of randomness whenever it's auto-regressively predicting these tokens. So there's this, if you have a temperature 1 versus a temperature 1.2, the temperature of 1.2 makes it a little bit more likely to just have a different token here, right? So rather than, hey, it was going to put a comma, but maybe it'll do something a little bit different, right? So what ends up happening when you do that? Well, the immediate thing is that the reward is actually lower, right? So actually, if you look at this, the reward initially is going to be worse, right? Because actually, most of the time, it's going to start fucking up, right? So it almost gets the correction or the thing correctly, but then that temperature 1.2 ends up putting some kind of weird token in here, and it ends up not even being correct Python anymore, right? So that's why it starts lower, but you could see it eventually kind of gets up here, and then it starts getting a little bit, like it still has to struggle against that kind of randomness as well, right? But it never actually reaches what this top one does, but I would say that's because it's still fucking up. So you can see here, you see these lines here at the bottom. Every time you see one of those big lines downwards, that means it basically produced something incorrect and it got a huge negative reward for it. So if you're at a temperature that is higher, you know, even if the model kind of already knows what it's outputting and it's outputting the right little matrix multiply kernel, because of that high temperature, it's going to put some weird shit in there and it's going to be failing, even though it's kind of smarter than this one, I would say, if you want to think of it that way. But the reason we do this is because we really want to kind of explore the space, right? Reinforcement learning is all about kind of the bitter lesson and using search to explore the search space faster, right? So one way you could do it is kind of lots of parallel, smaller, faster inference models, or you can kind of have more randomness in that, right? So maybe here's a little paragraph that comes from unsloth that explains this. Inference is crucial in RL training since we needed to generate candidate solutions before maximizing some reward function, right? So again, what we're doing here in GRPO is we're basically creating completions, and then we're using our reward function to grade those completions. So the speed at which you do inference is actually quite important because that determines how many completions you can have, right? So for example, that's actually what makes the huge difference with this H200 is that the H200 here, you can generate 128 solutions at a time, right? And that generation is batched, so that's where you get the speed up, right? The 3090 can only generate 2 completions at a time, right? Because it has a limited VRAM. So it has to generate the 2, then it has to evaluate with the reward function, push the gradient, then generate another 2. Then evaluate with the reward function, push the gradient, and evaluate another 2, right? So if you can get this inference instead to generate 120, right? Now you're going to have a much broader group so that whenever you do your group relative policy optimization, it's almost like you're taking this bigger batch size and you're kind of like that gradient is moving you in the correct direction more often than not, versus whenever you have these kind of very tiny batch sizes for something like RL with GRPO, your gradient is very noisy, right? Because it depends on these 2 that you sampled, and those 2 that you sampled might just be complete trash, especially if you have a high temperature, right? Julien confirming for us that most of the cooling is liquid cooling, but with some specifically designed oil. Actually, that's another cool rabbit hole of you guys. Oil-cooled PCs. This is something I've always wanted to do, but I've never actually done it, is there's this whole kind of internet community of people that will buy an aquarium and then fill it with mineral oil and then put their entire GPU inside the mineral oil. So they're basically using the same forced convection, using the same fan that normally would be used for blowing air through all your components, except in this case, it's blowing the mineral oil through all your components. And the mineral oil doesn't interact with the actual... So if you did this in water, right, it would just short and explode. But the mineral oil doesn't react, so you can actually do this. I think this is kind of a meme, to be honest. I don't think this is going to significantly improve your computer. From what I hear, kind of you just end up with a greasy, oily computer, and your room kind of smells greasy and oily, and it's kind of more just for internet points. But I could totally see some kind of special oil being used, and that refrigerant is like super poisonous. So you have to have all these kind of environmental kind of stuff related to that. So I think if you use something that's kind of more inert, like water, it's less damaging to the environment. So there's a couple different factors in there that determine that. Would it be better to have steps on x-axis instead of time? The H200 is likely going 8 times faster than the 3090. You are 100% correct. So here on the x-axis, this is time. So this makes it seem like, hey, actually the H200 is making kind of about the same progress here. But what Julien is saying here is that actually, if we change the x-axis to step, you see what's really happening here is that even though these two train for roughly the same amount of time, kind of like 20 hours, the H200 was able to produce a lot more steps, right? So the same, we're not, one way to say the H200 is better is because the VRAM is bigger, which means we can make the batch sizes bigger on the generation. Another way that the H200 is better than the 3090 is that literally the chips on there, those little streaming multiprocessors, they're just faster. There's more of them, so that the amount of compute it can do is more. So you can see in the same amount of time, it completed way more steps. Okay. We were reading this paragraph. To achieve the fastest inference speed, we rewrote Transformer's inference code and integrated many innovations, including custom algorithms. Okay, so this is kind of, now I want to kind of bring this into what exactly is unsloth, right? What exactly is thinking machines, right? Like what are these people selling here? And what they're really selling is software knowledge here. So there's two sources that I used for today's stream. There's this very nice blog post by Alexa Gordick, where he kind of goes super deep on GPUs and pretty much as deep as you can possibly go. And then there's this very nice webpage that someone shared on our Discord that goes through all the different kind of terms in the GPU world. Very nice little summary of all the different things here. But the memory in a GPU is highly hierarchical, much like in CPU architectures. So the hierarchy is dictated by physics and circuit design. SRAM cells are faster but larger, while DRAM cells are smaller and denser but slower. The result is that fast memory is lower capacity and expensive, while slower memory can be provided in much larger quantities. So this fundamental trade-off between capacity and latency is why cache hierarchies exist. So in an ideal world, every compute unit would sit next to a vast pool of ultra-fast memory. Since that's physically impossible, GPU designers compromise by putting small amounts of fast memory close to the compute and then progressively larger pools of slower memory further away, right? So when you actually look at a GPU like an H100 or an H200, what they actually are doing now is they are, let's see, texture, no, we want up here. Special core, load unit, CUDA core, tensor memory, tensor cluster, L1 data cache, register file. Where is it? Where's that picture? This is the picture. Okay, so in high-performance data center GPUs like the H100, RAM is located on a die directly next to the processors, right? So something that they're already doing here, right, is that you don't want to have to, the streaming multiprocessors here, this is the actual chip in the GPU, right? So imagine if the memory or the information had to go all the way out of the graphics card, through the PCI, into the CPU, into the RAM that the CPU has access to, then get the information from there and pipe it all the way back up. That's going to be pretty slow, right? So now we have this HBM, this high bandwidth memory, directly on the die, right? So what that actually looks like is this, right? So this chip right here, only that center part is the actual chip part that's actually doing the computation. This other part right here is actually just memory. The memory is baked into the actual chip. So kind of like the best way that I have of thinking about what this looks like is kind of like a city, right? Where like there's a limited place in a city. So as you move outwards from the city, you have more space, you have more houses, but then the houses that are closer to the inside of the city are kind of more availables, right? So there's this kind of hierarchy of residences in a city as you move away from the center part of the city. And it's kind of the same thing with the GPU. It's like there's kind of layers of memory that are closer and are right there, right next to the actual SMs or the chips. And then as you get further and further away, it gets easier and easier to have bigger and bigger pools of memory, but they get slower and slower to access, right? So fundamentally, one thing that I kind of want to point out here is that this problem will never be solved, and it will always be a pile of slop, right? So you have on one side, for example, here is the actual math equation for GRPO. And then on the other side, you have an actual GPU running that algorithm, right? And there's all these layers in between, right? So you can, at the lower level, you have things like the SAS and PTX. You get higher up, you get things like Triton, CUDA, and then eventually you start getting to the super high-level abstractions like Keras and Torch, right? But the problem is that every level of this is very complicated and very nuanced, right? So this is a kind of something I'm trying to show you here. This is in biology, right? This is an octopus eye versus a human eye. In the octopus eye, or in the human eye, everybody knows we have a blind spot. And the reason we have a blind spot is because the kind of cabling on these photoreceptor cells goes into the inside of the eye, which means that all that cabling needs to get now routed out of the eye. And in order to do that, it's going to create this hole, and that hole is the blind spot. So an octopus eye kind of has all the same things here. You have the lens, the iris, all these different things. But because of just this kind of choice of the cabling, now you don't have this blind spot. Right? Here's a similar kind of situation where every single mammal, I think it might just be, I don't know if it's just mammals, but every single mammal has these like really inefficient cable designs where, like, for example, you have a nerve that goes all the way underneath the aortic arch. Even something like a giraffe has this as well, which doesn't make any sense. But the reason this happens is because this kind of incrementalism creates slop, right? So, for example, here's an example of this in GPUs. So the single most common source of error when using cuBLAS is the matrix data layout. For historical reasons and to maintain compatibility with the original BLAS standard, which was written in Fortran, cuBLAS expects matrices to be in column major order, which is the opposite of the commonly used row major order in C, C++, and Python, right? So this is like basically the code equivalent of this, right? Where it's like some arbitrary decision that someone made 10 years ago now has kind of bubbled through this pile of slop over the years to result in all these kind of weird little nuances that mean that the previous layer also needs to account for those weird little nuances, and then the layer below that also needs to account for those weird little nuances. And ultimately, the current tech stack does not fit inside a single human brain. So to make progress, humans have to resort to incrementalism, right? Where the person who's trying to optimize this stuff is not familiar with this stuff, and the person who's trying to optimize this stuff is not familiar with this stuff. So each person can only kind of incrementally improve based on what's currently there. If you change too much, it all goes to shit, which is kind of the same thing here, right? If I were to come in here and change 10 of these numbers, I would probably get some garbage, right? So I can only change kind of one of these at a time, right? That's the way to improve this, is incrementally. Okay, let me change this to 2 and then run it and see what happens. Let me change this to 4 and run it and see what happens, right? But that kind of incrementalism is always going to lead to slop. And ultimately, what we really need is some kind of ASI to basically design the entire tech stack end to end. And I think in the future, some kind of superintelligence will have the context required to design a new end-to-end tech stack. But until then, we're going to have this kind of incrementalist slop that is just like patches on hacks on patches on hacks on top of each other all the way down the stack. And basically, that's what GPUs are now, right? It's just this kind of like massive jarble that effectively looks like this, just inside code space and hard hardware design space. I'm muted? Oh no. All right, guys. Embarrassing. Let me try again. I'm going to switch the microphones here. What about now? Is that a little bit better? Let's turn up the gate. What about now? Better? I've been back for a bit. Damn, I'm sorry, guys. That's embarrassing. Now we don't have anything. Oh no. Now good. Now good, but bad quality. Oh no. Oh no. A little bit better? The initial one was good? Yeah, the problem is that this microphone, like the connector failed. This thing bent and now it's touchy, so blah. Sound is lower now. Yeah, I'm trying to make it higher. I turned up the gain so you can see here. What you're looking for in a microphone is you don't want this red. The red means you're clipping. So in a microphone you can change this gain here to make it louder, but generally when you increase the gain it like distorts it. And that's actually what, like, for example, like metal music and stuff like that, like kind of that's what they're doing. They're just messing with like the gain, for example. Okay. I was going down this rant of how all this complexity in GPU design and kind of all the steps that go from math to actual hardware, all of this stuff is just a bunch of incrementalist slop that is impossible to fit in one human head. And that ultimately is where unsloth comes in, right? Is basically because this stuff is so complicated and so annoying, and there's so much nuance, and there's so many of these little tiny like one things that you need to kind of get correct, there's this opportunity for companies like Unsloth and companies like Thinking Machines to basically abstract some of that complexity away from you, right? And maybe let's actually look at exactly what Unsloth did here, because I think it's kind of interesting. So one of the actually, let me show this. Here's a nice little chart that shows the difference between bandwidth for different memory pools at different points in the hierarchy of the GPU, right? So we know that the memory is this highly hierarchical thing. I thought this was kind of interesting. So on-chip cache, 20 terabytes per second. So that's the cache on the actual chip, right? So the cache that's like literally on the same exact chip, that's going to give you your highest bandwidth, right? Versus the worst possible bandwidth is an HDD. So this is like a literal disk drive connected via SATA, which is like the old school cables. If any of you have built computers back in the day, you remember SATA cables. That's the worst, right? SSD with SATA, a little bit better, right? Solid state, a little bit faster, right? SSD with NVMe, a little bit faster, right? DDR5 on the Intel, so this is now going through the CPU. GDDR a little bit faster, HBM a little bit faster, right? So you can see how there's this very clear kind of relationship between how far away the memory is and how close the memory is and how much bandwidth you have, right? Yeah, okay. So we were talking about slop and about this problem here and about why is this random company Unsloth providing the notebook to train GPT OSS 20B, right? Like, why shouldn't OpenAI release this? Like, why are they not releasing that? Why is Thinking Machines releasing LoRA fine-tunes for Llama, right? Why isn't Meta doing that? But you can see here, one of the things that they solved is, let me go here. Where is it? Here. So
To achieve the fastest inference speed, we rewrote Transformer's inference code and integrated many innovations, including custom algorithms like flex attention. Our new inference code was evaluated against an optimized baseline and got 2x faster. VLLM, which is another popular kind of inference framework. So for example, whenever we did the Hugging Face GRPO, I think the way that they did it, it was like they had a VLLM on one of the 8x H100s, and then the other 7 were pushing gradients. So they had a kind of setup where 7 of the GPUs were pushing gradients, and then one of the GPUs was basically being used as an inference machine. In this case, we're doing it on one GPU, so the GPU is basically stopped while it's performing inference, and then it's going to push the gradients. So it's kind of alternating between the inference and training, right? So if you can make the inference faster, you make the training faster, and so on. But with unsloth, what they did is they allowed training at with the model quantized. So what the fuck does that actually mean? What that means is that this here load in 4-bit, right? So the model, when it's actually performing inference, you can quantize it, which means all the little weights, you're using a lower precision data type to represent them. That means that the model is going to fit in much lower memory, but it means it's going to be a little bit off, right? So normally, you wouldn't want to pay that price, right? So normally you would say, hey, I don't want the model to be slightly shittier at the cost of making it slightly faster and slightly more, or use less memory. But the reason it's okay for this is because we're doing GRPO and we're doing RL, right? So like already you kind of want a little bit of randomness, right? You're already kind of turning up this temperature to get a little bit more randomness. So if your model is heavily quantized when you're doing this inference and it's giving you some kind of slop sometimes, that's actually good because in a way it's actually helping you explore the space more completely, right? The variance is actually a benefit. So that's kind of an interesting thing to think about. Okay, another thing here. Most frameworks use flash attention 3 by default, but this causes an incorrect training loss. I was like, huh? What's going on here? So what they're pointing out is that actually the GPT OSS model uses attention sinks, right? So attention sinks are basically kind of a cheat code to reduce the size of this KV cache, right? So we all know that the hard part about attention is that it's a kind of a sequence to sequence thing, which means that you have this t squared, right? The length of the sequence squared, you have this quadratic computational scaling, right? So basically the longer you make the sequence, the more memory it's going to take, the longer it's going to take to produce the next token autoregressively, right? And the more memory it's going to take to hold all these little blue squares in your GPU memory. So one way you could do that is you could do window attention, which you're basically saying, okay, let's just throw away the old stuff, right? So like the beginning of the sequence, we kind of start forgetting it as we go deeper into the sequence. So we're really only doing the attention with kind of the most recent stuff. Obviously, that's not ideal because the whole point of attention is that you want every part of the sequence to pay attention to every other part of the sequence. So if you're cutting out the beginning part of the sequence, you know, you're definitely going to have an issue there, and that's what they show here with the PPL, the perplexity, which is kind of like intelligence if you want to think of it that way, right? So very high perplexity means kind of stupid, right? Is that what? Let me make sure PPL, yeah, perplexity, okay. So what people do now, or what at least what OpenAI is doing, is this attention sinks, where basically they create this column, right? That you could think of it. It's basically. So one way to think about what's happening here is like if you remember the streams we did about Mambas and SSMs, right? These RNNs, these type of linear attention models that have a hidden state that is kind of this lossy hidden state, but because it's always the same size, it allows you to basically get rid of this O of n squared trap, right? So an attention sink is basically that same kind of hack, but applied to standard attention, right? Where now, rather than having all these blue squares in memory, you just have to keep this yellow square in memory, but theoretically, the yellow square is not going to have the full kind of information that this blue squares are going to have, but it's a hell of a lot cheaper to just use this yellow square rather than all these blue squares. So you're saving memory, you're making it cheaper, but now you have this kind of like lossy kind of hidden state that's kind of trying to pack a lot of information in there, but in practice and empirically it works quite well. So that's why OpenAI decided to put it in their model. Okay, but now what's the issue? Now, actually, here's a little better explanation. Attention sync hypothesis. Language models can be pre-trained to require only an attention sync token for streaming deployment. So this attention sync is an extra learnable token at the beginning of all training samples that serve as a designated attention sync. And here's some examples. Visualization of the average attention logit. So the more red this is, it means the more that attention matters. Right? So you can see here, for example, all the blue is here, which means that the stuff at the beginning of the sequence is less important than the stuff kind of closer to the part of the sequence that you care about, right? But an interesting thing happens here where in this transformer model, right, which is a bunch of these transformer blocks stacked on top of each other, so the higher up you go in the model, right, which is kind of moving up from kind of low-level features to kind of more global high-level features, you can see that it starts using these attention syncs even more. So as you get to the highest layers, like layer 31, layer 23, it's like so much of the kind of attention logit mass is in that attention sync. So attention syncs make sense. It's a good idea that they put them in there, but nobody's really implemented this, right? When are you going to give us GPT OSS reinforcement learning? No answer from OpenAI. You have here TriDAO. This guy is literally the kernel god. This is the Mamba guy. So he's telling you there's currently no backward learnable sync in any implementation. Correct. Right? So what's happening here is that basically OpenAI decided to put attention syncs, right? So somebody at OpenAI who was basically living in this part of the world, right, the math part of the world, they said, okay, let's put the attention syncs. But then by the time they release this, nobody has gone down this cascade of slop here and implemented kind of this lower level stuff. And what unsloth did is basically that. They're like, okay, well, we're going to do that. We're going to implement this low level kernel for this attention sync. And that's why they have the best RL implementation for RL fine-tuning of GPT's open source model, which uses attention syncs, and that's why we're using them. It's a pretty long rant. I thought unsloth was a quantization library. They do have quantization, and they're good at it, right? They've built expertise into quantizing, which is why they're able to release this this GRPO for GPT OSS, and a big part of the story for this is the fact that they quantize the GPT OSS when it's doing inference, right? Which means that this part is faster, right? And it takes less memory, so you can have a bigger batch size on a smaller GPU. Can you make a review on foundation model for 6DOF object pose estimation? It's a very specific request. I don't think there's a foundation model for 6DOF object pose estimation. I think that 6DOF object pose estimation is something that you would probably, honestly, if you really wanted to do that, you would start from some pre-trained image encoder, pre-trained vision language model, and then basically fine-tune it for 6DOF pose estimation task. There is explicit 6DOF object pose estimation models, but I think we saw in last week's stream that a lot of these specialist computer vision models like bounding box detectors, segmentation models, pose estimators, those might all just disappear, and what we might end up with is video generation models being effectively fine-tuned for all these classic kind of narrow computer vision tasks. Hugging face kernels with flash attention 3 plus the attention 6 from the VLLM team. Sir Julien is saying that there is another implementation. But maybe that's a good point, Julien, to talk about how like this stuff is very ephemeral. You know what I'm saying? Like think about all the effort that unsloth went into creating this. As soon as you have the next version of this model, GPT OSS 2, maybe it's going to use a different little trick, which means you're going to have to write a different kernel, right? So this is kind of what I mean by it's just like it's always going to be slop. Because the hardware people who are designing the hardware aren't going to be able to predict the future of what this math stuff looks like, and the people who are doing the math stuff are never going to be able to predict the future of what the hardware stuff looks like. Right? So you always have these kind of siloed peoples working at individual levels of this tech stack, incrementally improving their particular part of the tech stack, but you never have this kind of global end-to-end design that's happening. Yeah. So I guess the question is like, I have a lot more faith in something like unsloth than I do in something like thinking machines, right? Because something like unsloth, I think it's like literally two brothers. It's like these two guys. This is probably a little bit bigger now. They probably have like maybe 10 people, probably less than 100 people. But they're not burning money, right? So like these guys, they're building expertise in-house. They have this intelligence that they can then use to then every time something new comes out, hey, they've done quantizations and custom kernels for the last 4 models, which means they're going to be pretty good at making something for the newest model. So really what they're playing on is this kind of expertise that they're building in-house, right? But I think in-house software expertise like that is slowly becoming less and less valuable as you have coding models that are getting closer and closer to just doing all of this, right? So the moat of a company that has basically software expertise goes down over time. So I think unsloth will make some money, but they're not going to make money 20 years from now, right? There's like a limited window where they can make money. Thinking machines is in the same exact situation where I think there's a very limited window where they can make money. Hey, we found this slightly better way of pushing LoRA gradients for this specific llama model, and we're building expertise in this. But the problem is these guys raise so much money that they're never gonna make that much. You know what I'm saying? It's like they're already dead. As soon as they raised that much money, they're never going to be able to grow into that, because this idea of kind of like software layering, of kind of like becoming experts in this slop has an expiration date. I don't know, maybe I'm getting a little bit high level here. Yeah, it's like you have to be careful. You can't raise too much money. If you raise too much money, you can easily die, because you're never going to be able to grow into that. Okay. Yeah, let's maybe talk about this. This is a couple graphs that I thought were kind of interesting. So this is from special. Let me actually go here. Here we have performance in flops per second, which is actually, according to Alexa, incorrect here. He actually has a little point here, which I thought was kind of interesting. Flop versus flops versus flops versus flops. So flop is a single floating point operation. Flops with the per second is a floating point operations per second. Flops with a lowercase s but without this slash is the plural of flops. So is this correct? Flops per second? Kind of, yeah. I guess that's correct. But you can see here how there's this kind of almost like, I want to say Pareto frontier, but it's not quite the right term there. But you can see how there's two different bottlenecks in a GPU. There's kind of what I call space slop and time slop, right? So space slop happens when you have not enough space or area to put in your information, right? So like, let's go back to our matrix multiply. There's some size to these matrices, right? Each one of these little numbers is going to be, so the way that GPUs do this, not in sequence, like a CPU, is that think about if you had this exact same nested for loop, but rather than one CPU doing every single part of this nested for loop, you had 20 streaming multiprocessors doing each index of that nested for loop, right? But what that means is that now there's this kind of like connection or relationship between the hardware itself and the actual ability to do this, right? So like here, there's no issue since 32 divides 4096 evenly. If the matrix size was 33 by 33, then roughly 75% of the threads would end up doing no useful work, right? So he calls this tile quantization, but basically it's like when the size of the kind of memory and the tensor, right, those have some limited size depending on the hardware. When those just happen to not line up with the data that you're feeding in, then you have this kind of space slop, right, which is wasted compute. So that's one way that GPUs are inefficient, right? And that's basically here, this kind of memory bandwidth, I guess, because this slop means that you're going to have to store it in a memory pool and then bring it back, calculate it, put it back into the memory pool, right? So sometimes you're kind of memory bound, right, which means that if only I had more memory closer, I would be able to make more progress, right? Then you have kind of time slop, which is just like tile quantization. There's also the concept of wave quantization. This effect is noticeable when the number of waves is small. So in this case, waves is kind of like the time of the computation, right? So the computation does one thing, then the next thing, the next thing. So let's say you had to calculate 115 things, but your thing only fits 114. What's going to end up happening is that you're going to calculate 114 of them in parallel, and then you're going to have another step after that where you just calculate one, and the other ones are sitting empty, right? So you're effectively kind of doubling the number of waves, and one of them just has all this wasted, I guess, space, but in this case it's resulting in having time wasted. So this is these are not exactly the same thing, but this is the other potential limit of a GPU, is this compute bound, right? Where now the limit is actually the little chips or the streaming multiprocessors, like they just simply can't, my memory bandwidth is high enough that I'm feeding them all the information they need. They just can't actually literally do the computation fast enough. So sometimes it's memory bandwidth, right? So for example, the paper that we were looking at where they were looking at inference clusters, right? And they separate out the prefill versus the autoregressive kind of next token prediction, right? So prefill decode, right? So the prefill is when you calculate this giant KV cache. That is going to have a different pattern in terms of this memory bound and compute bound compared to the actual autoregressive prediction of the tokens, right? So maybe in the future we end up having hardware that's designed specifically for each of those, and that's actually what I think Elon was talking about. He mentioned this, and generally whenever Elon says something, it's not because he actually came up with that himself. It's because he gets to sit in a bunch of meeting rooms with incredibly smart people, and then that incredibly smart person tells him something, right? So like, so he went to an XAI meeting and he sat in that meeting room, and there was some guy who's an expert on GPUs who sat there and told him, hey, actually, there's this interesting kind of compute-bound, memory-bound situation where maybe we're going to have specialized chips for prefill, and then chips that have that are basically pushing on this side and trying to get the memory bandwidth as fast as possible, and there's going to be chips that are trying to get this arithmetic or compute bandwidth as high as possible, and that's going to kind of cause this speciation in hardware design, right? So that's the result of some of this. And then think about that even more. If we have a speciation event in terms of GPU hardware design, then now you effectively just doubled this, right? Now imagine having this, right? Where like you have like a second arrow, right? So now in these GitHub issues, someone's asking tried out, hey, so we have the flash attention implemented for the inference chip, but do we have the flash attention implemented for the training chip? And this guy's, no, not yet, right? So it gets even more crazy. Here's another kind of interesting picture. I've shown this one before, but this is kind of the same idea of compute bound, which is computational performance flops per second, versus memory bandwidth or interconnect bandwidth bytes per second. And you can see here how we're already kind of starting to see this I call it speciation, but you see this H100 versus H20 slightly different designs, right? I think this gets even more exaggerated, and you end up with kind of specialized inference, specialized training, right? What else do I have here? Talked about that. There's a couple other things that I wanted to think about here. Yeah, here's actually an interesting peak rate. So this is the number that you see on, for example, NVIDIA's pages, right? NVIDIA H100 GPU with 132 streaming multiprocessors, each containing 128 FP32 cores, can issue one precision fused multiply add, right? This fused multiply add, that's really the holy grail. Obviously, we're doing it in Python, which is kind of just nonsense, but it's basically if we can improve this matmul and we can find a better matmul, because it's such a big part of every single part of the transformer, then it's a very good representative of like what are you actually going to be running. So if your GPU does this FMA fast, then it's probably going to do everything fast. So it ends up being 33,000 instructions per clock, right? And the per clock there kind of goes back to what I was saying here with the time slop, right? Where the clock on your GPU is executing operations. So that's basically the speed of this T0, T1, T2. That's your clock speed, right? And the clock speed also kind of, you can change that, right? So for example, your CPU, when you get it, has a specific clock speed. You could take that clock speed and you could overclock it, which means making that speed higher, which basically means increasing the speed of this T0, T1, T2. But the problem with that is then you're trading off lifetime usually. Usually if you increase that speed and you overclock it, it's going to start overheating. Now you potentially need to do this mineral oil PC stuff or like add liquid cooling. And if you're talking about data centers, now you have to start thinking about, okay, well, if I overclock it, it's going to reduce the lifetime of this chip, and like I have some amortized cost that I paid $30,000 for this GPU, and now I need to sell it for $2 an hour. So there's a lot of kind of complicated finance there. But you take that, the H100 can operate its compute subsystem clock at a maximum rate of 1,980 millihertz. So the peak rate is basically how many FMAs can you do with all your cores at the highest clock rate, and that's where you get the 66.9 teraflops. But this is basically not representative of the actual compute that you can do. And I've seen the argument for this being a better metric than all these other things here, right? So if you actually go here to our WANB, let's actually turn on all of these, visualize all. We look at our system. Can I make that small? Nope. Can I reduce the size of this? Ugh. Finally hitting issues with this big mouse. Oh my god. Alright, let's actually just look at this. You got GPU power usage, not super indicative of whether or not you're actually utilizing your GPU effectively, right? GPU memory allocated percent, also not necessarily super efficient, or not necessarily a super indicative metric, right? GPU utilization, GPU time spent accessing memory. These are all different things that give you an idea of where you are from a GPU performance standpoint, but they're not really the most important thing. So some people are talking about this MFA GPU metric. Model flops utilization as the ultimate thing that you should look at. Disk utilization. Process CPU threads in use. What is this one? Yeah, so you can see, for example, the number of threads on this 3090 way lower than the number of threads on this H200. System memory utilization, right? So none of these are using the system memory very much, but that's actually a good thing, right? You don't want high system memory utilization because it just basically means that you're storing a bunch of crap into the system memory that you probably shouldn't be storing there anyways. A simple question. For quantum computers, because I believe they are more powerful than regular GPUs. Yeah, I mean, on paper, quantum computers are very good, but the reality is that they're not, they're basically just vaporware, you know? And like the thing with a quantum computer's error correction. It's like they don't really work. So basically they have to come up with these ways to correct the final solution. And even then it just seems a little sketch. And even then, once you design quantum computers and you have better quantum computers here, you basically need to redesign this entire stack, which can be very difficult to do. So I don't know. I don't think quantum computers are going to be here in 5 years. And because they're not going to be here in 5 years, I think that we're not going to have to worry about them because some future ASI will basically solve quantum computers for us. I don't think humans are going to solve quantum computers. I think superintelligence is going to solve quantum computers. It's just we've been trying for like decades and it's just not there. It's all just demos, and the demos, raise money, and then they try to like position themselves and pretend that like, oh, you're too stupid to understand quantum computers. It's like, no, they just don't really work, Would be interesting what the thermodynamic computer. Yeah, that's another cool one. We reviewed a couple papers on that. That's also a slightly different stack. But actually, this one was kind of interesting for quantum or for thermodynamic computers. It's like a completely random paper. This one here. Yeah, I was looking at this paper yesterday. This is another kind of weird non-transformer architecture. They call it BDH. It's basically, here's the actual, so you have what they call local mean field dynamics. So you basically have like neurons in the brain, right? There's no kind of clock in the brain. It's not like there's this clock that's kind of orchestrating everything, and you're basically calculating the things at one layer of neurons, and that feeds the next layer of neurons, and that feeds the next layer of neurons. The brain is kind of way weirder than that, right? You just have a bunch of neurons. They're all connected together. The intelligence is in this kind of weird connectivity, what they call Hebbian learning here, right? So the brain is intelligent based on some kind of spiking graph dynamics. That basically means that there's this graph, all the neurons are connected in this graph, and then whenever one neuron kind of reaches a certain threshold, it spikes. That sends signal to other neurons. There's inhibitory neurons. There's all these weird complexities, and somehow we get human intelligence and consciousness out of that, which is kind of crazy. These guys are basically trying to argue that, hey, let's try to replicate that weird kind of like graph dynamics rather than doing what we do now, which is this KV cache into MLPs, this kind of like almost like clock, kind of very, very, very hard coded to the specific kind of binary computer system that we have now compared to something a little bit more brain-like. But the reason I guess I'm talking about this is because I feel like this type of stuff might actually work well with the thermodynamic computer, right? So we might end up in a different world where we have these different algorithms that operate on the thermodynamic computers with a completely different stack, right? So you might have kind of this classic stack, and then you'll have a slightly different stack that uses slightly different algorithms on slightly different chips, and then a whole cascade of stuff in between then, and then companies that kind of pop up to provide kind of the software layers in between those. So what might be possible by just scaling photonics computing is likely enough for a new industrial revolution. Yeah, photonics computing is basically kind of going all in on the kind of fiber optics, using light. But I think they use them for a lot of these data centers, like the interconnects between these are optical. So it's like they're already using light-based communication to communicate more rapidly between these, right? So you're basically trying to solve this problem here that we looked at, this one here, right? So optical interconnects basically increase this networking bandwidth, right? So this is older now, but you see your GPU connected to your CPU, then that GPU has to go through the PCIe to actually get to the CPU, and then you have to go through these NV switches to connect to each other, right? So like let's say you had some kind of model parallelism or tensor parallelism, you were storing things in two different GPUs. At some point they have to communicate. You have to go into the network through an Ethernet cable into the other GPU. So an optical interconnect is basically saying, hey, rather than going through the Ethernet cable and then through this like old school router, we actually go through this basically fiber optic router, and it's faster. Chinese are very good at photonics. I could see that. I'm not like a photonics expert by any sense of the word, so. Beth must know a thing or two having worked with quantum tensors. Probably. I would say Beth is the Extropic founder. But yeah, he probably definitely knows a lot more about optical interconnects than I do, for sure. Europe is second, and then the US last. I mean, like, people love to shit on Europe, but like, ASML is from Europe. Like, let's not forget that when it comes to the most like dark magic of all the dark magic, like ASML is the alien technology. Like this is the type of shit that like nobody understands this, you know? Like there isn't a single human being on planet Earth that could build one of these ASML machines from scratch. And that's in Europe, right? And then actually I think like they just bought Mistral stock as well, so basically now they're kind of all in the same bucket, but yeah, Europe is secretly the highest level wizard here, you know? But they're fucking up other things, I suppose. Okay, let me see what else I wanted to show you guys today. Yeah, I think I showed you guys this already, but the fact that like these two random brothers were able to create a faster and non-buggy version of the OpenAI attention sync kernel. That's hardcore. I think we talked about that. We talked about the kind of complicated reward function. Oh, this is related to kind of the temperature conversation we were having. But one thing, the reason reinforcement learning works is because of search, right? RL only works because search works, right? What you're really doing in RL is you're going out and you're trying to find the right answer. And then once you kind of find the right answer, you kind of push gradients that make the model do that more, right? We're still very much in this paradigm, which means that a lot of the RL right now is just about finding these negative paths and closing them. But I'm a believer in scaling reinforcement learning. I think with AlphaGo and some of these other projects, we've seen that you can have something that looks more like this, where the majority of the compute is coming from reinforcement learning, and it actually ends up being more intelligent than something like this. So I think we're just in the beginning of RL, but an important thing about RL is increasing the number of rollouts and exhaustively broadening the exploration, right? So performance plateaus after 1,000 steps with clear diminishing returns from allocating more computation to additional training. What does that look like? That looks a lot like our training curves, right? Isn't that, it kind of feels like that's what's happening here, right? We have this kind of plateau that happens because really you just kind of learn to not fuck up, and then at some point it's going to be very difficult to get this to kind of explore more of the space of possible matmul kernels, because it's already kind of like you're narrowing it and narrowing it and narrowing it. So how do we broaden this exploration, right? As the number of rollouts per prompt increases, the influence of the unsampled terms diminishes, driving the overall effect towards Q positive greater than 0. So the correct token probability mass increases. So most of this paper is just kind of this like theoretical kind of grounding to it. But basically what they're trying to, the main learning here in this paper is that you want this number here, num generations, to be as big as possible, right? Which kind of matches a lot of the intuition that we already had around batch size, where if you keep increasing the batch size, your gradients become more stable because they're more representative of like kind of the actual full data distribution, if you want to think of it that way. So same thing with RL, especially now that we're using something like GRPO where we're doing this group relative stuff, increasing that kind of like batch size or the amount of rollouts, right? So basically how many generations you have in this inference is going to increase that, right? Here's a little tip. Learning rate was scaled proportionally to the square root of the increase in batch size. So if you have an initial base learning rate and an initial batch size, then the new learning rate for the larger batch size, you can base it off this, right? And that's actually, for example, if we came here, right? So now we have 2 generations. Kind of think of it as the batch size, and you have this learning rate. So if we basically increase this to 128, we would probably also want to increase this learning rate, right? So huge batch size, big learning rate. Small batch size, small learning rate. What about this? This was an interesting paper, but it's basically just talking about how like all the file formats that we use right now are garbage. People are still using V1 Parquet, which was made in 2013, and it's saying that now that kind of we're in a different computational paradigm, and also we're dealing with different types of data, that we should actually rethink about our file formats. So I kind of 100% agree with this, but it's going to be difficult to convince people to actually do that. What is this? Oh, this is another interest. This was the Hugging Face best paper yesterday or something like that. But here you have the concept of a frame sync, right? So very, very similar. I thought it was interesting that we now know that OpenAI is using attention sinks, right? And now here's this paper out of NVIDIA that's using what they call a frame sync. So basically the same thing, but for video generation. So that's pretty good, because what that tells you is that, okay, well now this implementation that unsloth made for attention sync can now be potentially used for this type of stuff here, right? Yeah, this paper is pretty cool too, because it's basically they're doing video generation with multiple prompts. So basically, rather than one prompt and then that prompt is basically used in this attention operation with the entire generated video, you instead have multiple prompts so that you can change the video. But the way that they do that is with this frame sync and then short window attention, which is kind of like not paying attention to the earlier part. KV cache re-caching to maintain adherence across prompt switches. Which to me almost seems like we're kind of like we're deriving Mambas from scratch. You know what I'm saying? It's like Mambas came out and then people were like, yeah, this is better, but we don't want to switch. We have all this shit already implemented for transformers. It's kind of too annoying to switch to Mambas. And now suddenly it's like, oh, well, we're going to start using attention sinks. And it's like, okay, that's basically just the hidden state in a Mamba. IDK. What else? Anything else people want to talk about? Oh no, look at that. Unfortunate. This purple one is the one that was running last night. And I left it basically here. Like I went to sleep right here and I was like, this is going to be so good. I'm going to wake up and it's going to cross this orange line. But it never did. You see? Failed, goes down, goes back up, and it almost looks like it's going to cross it. No, it goes back down. I guess it just didn't have it. I guess just fighting that temperature 1.2 was just too much. Right? And actually I have a temperature 1.8. Look at this one. So, boom, 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 boom. Let me visualize none. Then visualize this one. The temperature 1.2 or 1.8. This one, look at the train reward. It's just always trash. You can't learn. You know, you're always getting just a massive negative reward because the temperature is so high that all the things that it generates are basically, it's very difficult for it to generate something that is even correct. Which means that we'd probably want to turn the temperature down a little bit and probably adjust some of these. For example, this one here somehow. But the problem is as soon as you start messing with these reward functions, it becomes impossible to compare. Right? Because all of these are using the same reward function. But if I change the reward for getting it wrong, suddenly this purple line might be way higher than this orange line. I think it's way better, but it's not way better. It's just because I changed this no cheating score from maybe -20 to -10. Right? So, gnarly. What's your day job? Actually, that's a very good transition, Mass Laxi. This is going to be my last stream for a good while, you know. I did accept a position somewhere. They asked me not to share, but it is something super cool. And I'm going to be kind of working heads down on that for a while now, so we'll see where that goes. And I'm probably not going to be streaming while I'm working there. So, yeah, it should be cool. We'll see. I'm definitely excited. But maybe I'll stream on the weekends, you know? Maybe I'll do like weekend streams. Yeah, robotics, but I feel like I'm going to start giving away too much information. Depression? Don't be depressed, man. It's not worth it. You can take up the mantle, dude. There's way better YouTube channels for this type of stuff, to be honest. You know, I think it's just nothing is forever, and I feel like to me it's like we're already kind of past the golden age of streaming. You know, I feel like I'm looking at a lot of these YouTube channels. There's a lot of AI generated content out there. Just the professionalism on YouTube is also much higher, you know, so other people that do similar content to me, it's like they have like B-roll, they're editing, they're doing so many kind of fancy things. It's like I'm just not staying up to date, right? It's like I don't generate anything. I really don't do any editing, you know, so I feel like I can't this is kind of already dying. You see what I'm saying? Are you still active on Discord? Yeah, I'll probably still drop by. But I do not necessarily endorse anything on my Discord. You know, I don't control. I'm not very authoritarian about the Discord. So it's basically just like a bunch of random people just saying random things. It's a lot of cool people on there that say a lot of cool things, but, you know, like, don't get pissed at me if there's weird stuff on there. Because I don't control them. Okay, what else was there that I wanted to talk about? Oh, here's a paper that came out basically super recently that's effectively this exact thing, towards robust agentic CUDA kernel benchmarking, verification, and optimization. So this is a slightly different approach here where you aren't using RL directly, right? So like this GRPO training that we're doing here is basically alternating inference and training. And ultimately, we're using GRPO to push gradients into a LoRA on this model, right? And we're running into all the kind of issues of just like, hey, the LoRA has a limited capacity. RL kind of has this kind of weird phenotype of basically closing down your model generation space. It kind of just becomes more narrow. But a completely different, we have the temperature problem where if you sample if you make the temperature too high, it just kind of is not the right type of randomness. It just kind of does random individual tokens, but it's not really the type of randomness that you want, which is kind of similar to kind of robotics, right? Where if you just kind of naively apply randomization on top of your RL, where just like the robot just kind of like vibrates, that's not going to necessarily be the type of exploration that allows you to find those more optimal policies. So a completely different approach to solving this kind of kernel optimization is using kind of a more agentic framework where you have agents that are going out and basically exploring the space of possible kernels, and then you're filtering those down into some kind of data set, and then you use that to actually either improve the model and push gradients into the model, or you're improving the prompt, right? That's another thing that this doesn't even think at all about. Is like, hey, we're pushing gradients into this model, but like a lot of the performance of this is this prompt. So shouldn't we be using kind of this iterative generation and validation and generation and validation to improve this prompt too? So I think there's probably better ideas here on how to do this type of kernel optimization with kind of agent loops as opposed to what we're doing here with basically like pushing gradients directly into the model itself. What? Thank you for the presentation. Very enlightening. I appreciate it. By removing parts of the LLM, do you mean increase the sparsity of the model? Sparsity is kind of a super overloaded term. Like the original sparsity neural net, the original meaning of sparsity is basically this, where, hey, you have a fully connected neural net. Is there a more sparse version of that where the connectivity is a subset of the densely connected version, right? So you have less connections. And this is actually what the lottery ticket hypothesis was basically saying, hey, actually you can get rid of a bunch of these weights and the model is kind of the same. And that's why people were excited about this. It's also because of this you need less memory, less compute. But now people use sparsity to also talk about, for example, mixture of experts models, which have multiple FFNs, and then you have some of them that are active and some of them that are not active. So they would call that, oh, that's kind of sparse because it's like it's not using all the weights, it's only using a subset of the weights. But yeah, I would say sparsity is an interesting thing to look at, but it's pretty broad. There's lots of different types of sparsity now. All right. Oil computers, model flop utilization, quantum computer error correction, and ASML alien technology. Kind of summarizes the stream, right? All right. Let me see. I think that's pretty much everything I had. Oh, I thought, here's something to think about. This is a quote from someone in our Discord that summarizes this paper. Lost landscapes are all you need. Neural network generalization can be explained without the implicit bias of gradient descent. If you have a large model and you randomly sample the parameter space until you get a low loss, then that solution is very likely to generalize well. This suggests that for over-parameterized models, good solutions occupy more of the lost landscape than bad solutions. So this is kind of an update on my intuition that I feel like I've had recently, where it's like, first of all, over-parameterized models, every single model we use right now is over-parameterized, right? These giant transformers with billions of parameters, these are all over-parameterized models. So maybe this intuition that we all have about like this lost landscape, which is basically what you're doing with gradient descent, is you're basically taking little steps in this lost landscape, right? So big learning rate means big steps, small learning rate means small steps, and ultimately you're kind of relying on gradient descent, which is kind of telling you the gradient at that instantaneous point for that batch is telling you go that way, right? There's this kind of assumption that we have that there's this kind of global optimal global minima, right? So it's like the lost landscape is this giant toilet bowl which kind of just drains you to the bottom, right? But maybe that's not actually a good intuition, and maybe what we're really dealing with kind of looks more like this, right? Where it's like there's a lot of minima, and they're all kind of about the same. So when I'm using this LoRA with a really tiny learning rate and adjusting the model ever so slightly, it's like I'm kind of going here, and I'm just going like boop, boop, and I'm just going to one that's like right next to it. That's kind of about the same, right? So what is the interaction with RL with these type of overparameterized models when the loss landscape is mostly all the same? I don't know. I'm just kind of putting that out there to think about. Okay, I think that's pretty much everything I had. Use your free credits, by the way, guys. Use those free credits. Get that GPU running. Go into Iceland. Let's see actually where this is. ICE01. ICE01 data center. Here we go. It's a 3 megawatt data center. Look at that. It looks like some kind of Arctic research station. Looks pretty badass. Let's see. Is it by a volcano? No, it's not by a volcano. It's a little bit it's just in the main city here, Reykjavik. This is where you fly into. That would have been pretty cool if it was like somewhere here, like these weird glacier areas. I mean, it's Iceland. It's very small, so it's close to a volcano anyways. You're always close to a volcano in Iceland. Maybe that's really the truth. Alright guys, that's pretty much everything I have. I'm just gonna... I feel like I already summarized this, but you can find all of this on my Hupo docs GitHub repo. So here's the code, right? So this is basically just I took the unsloth notebook and then basically just turned it into a Python file and then just pulled up all the configs here so you can kind of mess with these configs. I also have the Wanbi, so this is public, so if you want to go and you want to look at some of these, you can go ahead and look at that as well. But that's pretty much it, guys. GPUs are this giant pile of slop. We're never going to really solve this problem. It's basically like this weird slop that we have in our body, right? Or the slop and inefficient design that we have in our system. This same kind of incrementalism of evolution and incrementalism of building is basically exactly the problem that we have in deep learning, where it's just like every single part here has all these weird caveats. They've all kind of been designed in silos just because nobody's ever been able to kind of fit the whole thing end to end in their head. So we kind of have this like really sloppy pile of crap, which leaves opportunity for companies like Unsloth or companies like Thinking Machines to basically say, hey, well, we're going to create one particular path through this pile of slop that is slightly more optimal than the path that is currently there. But I think over time these business models kind of erode because of coding models are just so good that they basically just do it for you. Alright, that's my doomer take, but I appreciate everybody. Thank you for listening to these streams. I appreciate the journey. I'm probably not going to be streaming for a little while, but I would definitely not despair from that because I think there's more than enough ML content on YouTube to satisfy you guys. So thanks for everything. I appreciate it. Thank you, Julien, Saskia, Ruslan, Maslax, Aries, James McLean, Jamal, Bigfoot, Every Dream AI. Who else? If I miss your name, I'm sorry here. Mickey, Tamiru, Badge and Gun, uh, Winavin, 770, Miss Masokoko, and Open Room XYZ. Thanks everybody for hanging out. Hope you guys have a good weekend and see you guys at some other point in the future.